Welcome back. We are now into part C, 6C. Like I told you before, we will continue doing the same methodology that we used before. We're just using it for something different this time. So this time we're going to go from the molecular formula to actually talk about the atoms inside the molecular formula or the elements. So the objectives are going to be to convert from moles of a compound to moles of the elements that made the compound. Then we're going to go from grams of the compound to grams of the element that made the compound. And if you do it one way, you should be able to do it backwards. So let's begin with this problem. This problem is asking to find out which one of these four compounds contain the bigger number of moles of oxygen. For that, we have to look at the formula of each one of them. For example, on water, we have one oxygen or 1 mole of oxygen for every 1 mole of water. Basically, one of these for one of these. For hydrogen peroxide, we're going to have 2 moles of oxygen for every 1 mole of hydrogen peroxide. If you notice, I went from this relationship to a conversion factor, which will be the same as 1 mole of hydrogen peroxide for every 2 moles of oxygen that it contains. And it's talking about 1 mole of this for every 2 of these. When we talk about sodium nitrate, then we have 3 moles of oxygen for every 1 mole of sodium nitrate. So we're doing nothing more than building conversion factors. That's all we're doing. And you're already familiar with conversion factors, right? And the last one, we're going to do carbon nitrate. And we're going to see that we have 2 of these, which means we have how many? We have 6 moles of oxygen for every 1 mole of calcium nitrate. So that's how we're going to approach that. So let's go ahead and do that. Let me clear the screen real quick. So let's see how many moles of oxygen. So given 2.3 moles of water, how many moles of oxygen would that be? Well, let's set it up like we are. No, we do not want the moles of water because we want the moles of oxygen, right? And according to the formula, you got for every 1 of water, you have 1 of oxygen. So the first one is going to be 2.3 moles of oxygen. Let's do the second one. So for the second one, we're going to have 1.2 moles of hydrogen peroxide, and we want to know the moles of oxygen, which means I do not want the moles of hydrogen peroxide, so put it at the bottom so I can cancel it, because I want the moles of oxygen. And according to hydrogen peroxide formula, I'm going to have 2 moles of oxygen for every 1 mole of the molecule, which means I have 2.4 moles of oxygen. So this one is going to be 2.4. What about the next one? The next one, I'm beginning with 0.97 moles of sodium nitrate, and I need to know how many moles of oxygen I'm gonna get, which means I do not want the moles of sodium nitrate because I need the moles of oxygen. And according to the formula, I have 3 moles of oxygen for every 1 mole of that, which gives me 2.7 moles of oxygen. And the last one will be 0.5 moles of calcium nitrate. And with that, I need to find out the moles of oxygen, which means I do not want the moles of calcium nitrate because I'm looking for the moles of oxygen. And according to the calcium nitrate formula, I have 6 mole of oxygen for every 1 mole of those, which means I'm going to have 3.0. Therefore, which one contains the number moles of oxygen given those formulas and quantities? The answer will be calcium nitrate with 3.0. So basically, the purpose of this particular learning check was to see that you can get a conversion factor just by looking at the formula and the atoms or the subscripts that the formula shows you. So with that, you can do that daily work. So we're looking for the moles of hydrogen in this case. So let's move into something else. So if I give you the grams of a chlorofluorocarbon compound, which are what A or B are because they contain chloro, fluorine, and carbon. If I give you that each one of them is 38 grams, can you tell me how many grams of chlorine only I will get? Which means I need to go from the grams of the compound, right, to the grams of the element. Which means I'm going to have to go first to the moles of the compounds so I can use the conversion factor that I just showed you in the previous problem to go to the moles of the element, and from there I will get to the element. So for the first one, I would use the molar mass straight from the periodic table of the compound, right? Then I would use the conversion factor from the formula, just like we did on the previous problem. And then I would use the atomic mass from the periodic table to do the last step. So let's go ahead and do that. And I already have conveniently located the molar mass of the compound that I'm talking about. So let's do that. So given 38.0 grams of CF2Cl2, can you find the grams of chlorine on this case? Well, I can never go from grams to grams. I'm gonna have to always go to the moles first. So I don't want the grams of CF2Cl2 because I need to know the moles first, CF2Cl2. But I do not want the moles either of CF2, so I'm gonna get rid of it, because I really need to know the moles of chlorine. That's what I'm looking for. Which means I do not want the moles of chlorine, because really what I need is the grams of chlorine. And that should give me the grams of chlorine. So the only unit remaining is the grams of chlorine. If you notice, I haven't put any numbers. I just did the unit first. That's what we call this dimensional analysis or train track. So what goes on the first conversion factor is the molar mass of the compound, right? So the molar mass of the compound is 1 mole equals 120.9 grams. What about the second conversion factor, moles of chlorine to the moles of the other one? Just like we did on the other problem, we have 2 moles of chlorine for every 1 mole of this. So 2 of chlorine for every 1 mole of this. And now the last one is just the periodic table. How much does a chlorine weight? 1 mole of chlorine weighs 35.5 grams according to the periodic table. So at this point, all I have to do is 38.0 times 1 times 2 times 38.5 divided by 120.9 divided by 1 divided by 1. And that will give me my result. So let's do the second one. So for the second one, we're gonna have once more 38 grams of the compound, the new compound, C2F3Cl3. And at the end, I will want the grams of chlorine only. I can never go from grams to grams. I always have to go through the moles. So I do not want the grams of C2F3Cl3 because I'm actually looking for the moles of C2F3Cl3. So that will take care of the grams. But I don't really need the moles of C2F3Cl3 because what I really need are the moles of chlorine. But I do not really want the moles of chlorine because I'm actually looking for the grams of chlorine. And that will allow me to end up with only one unit, the one I'm looking for. So the first one is the molar mass of the compound, which is given right there. So that would be 187.4. The other one is the moles of chlorine based on the formula. So we have 3 moles of chlorine for every one of these, which means for every one of the compound, I have 3 of the chlorine. And once more, we know that the atomic mass unit for chlorine is 35.5. And that will give me the setup to go from grams of one compound to grams of the elements inside that compound. And you can do that for chlorine, you can do it for carbon, you can do it for fluorine. So I think you're ready now to do your daily work. So that's your daily work, A, B, and C. What about something like this? So iron, so that's the element we're dealing with, right? Iron, Fe, is found in the Earth crust as several different iron compounds. So we know that iron is a transition metal. So we know that iron can have multiple ions like Fe2 plus, Fe3 plus. So you're gonna find different combinations of compounds with different cations of the iron. So for this problem, we want to calculate the mass. So we're looking for the mass, but we want it in kilograms, not just in grams, but in kilograms, of each compound that contains this much iron. So a sample of this will contain 1.10 to the third kilograms of iron. That's a lot of iron. And a sample of this, even though they're different, we're talking about the same amount. The question is, what would be the mass of the compound? So we're going from the element now to the compound. Before, we were doing from the compound to the element. Same thing, we just have to make sure that we cancel what we need to cancel. So given 1 times to the 3 grams of iron, can you find how many grams of the compound, right? Fe2O3. You will, it will have to weigh to contain that amount of iron. So we cannot go from grams to grams. We're gonna have to go from grams to moles, and then from moles to grams, which means I do not want the grams of iron, because like I told you, I need the moles of iron first. And once I do that, I do not want the moles of iron either, because I'm really looking for the moles of the compound, right? That's why I'm dealing with this. However, I really do not want the moles of the compounds, because what I'm really looking for is the grams of the compound. And now I just fill up the numbers. The first one is the atomic mass unit, or the molar mass of iron. So 1 mole of iron is going to be, I do not know that from memory, so give me a second. 1 mole of iron is going to be 55.85 grams. And then how does the iron relate to the compound? So this is the compound, which tells me 2 moles of iron for every one of these. So 2 moles of iron for every one of these. And then I have to go to the molar mass of the compound, which I conveniently have found ahead of time, which is 1 mole equals 159.7. And then all I have to do is 1 times 10 to the third, multiply by 1, multiply by 1, multiply by 159.7, divided by 55.85, divided by 2, and divided by 1. Multiply everything on top, divide by everything at the bottom. And that's how we'll approach this one. Let's do another one. So the next one, so we did that one already. The next one is given 1.010 to the third, right? 10 to the third of iron. Actually, this were, I apologize. These were kilograms. I forgot about that part. So make sure you multiply by 1,000 on the last one. So let me show you how we set it up. So we had that many kilograms of that, and given that, we want to find the grams of the compound, which is going to be FeCO3, or iron Roman number 2 carbonate. So how are we going to do that? Remember, we cannot go from grams to grams. We have to go through the moles first, but to go to the moles, like I just said, we have to go from grams. So we don't want the kilograms, because we need the grams. And these are the grams of iron and kilograms of iron. So that will give me the grams of iron, but I do not want the grams of iron, because I cannot do anything with that. I'm gonna need the moles of iron. but I really cannot do much with the moles of iron because I'm really looking for the moles of the compound, which is FeCO3. But that's not really what I need, because in reality, the problem is asking me to find the grams of FeCO3, and the problem is actually asking me to find it in kilograms. So I'm gonna have to do one more step. So I do not want the grams, because I want the kilograms. If you notice, just with this setup, we're gonna see that the kilograms is canceling everywhere almost toward the end. So what about the numbers? Well, the first one is just kilograms to grams. So 1 kilograms equals 1,000 grams. The next one is the molar mass of iron, which I told you is 1 mole for every 55.85 grams. The next one is the formula, which tells me I have 1 mole of iron for every 1 mole of this. So it's 1 to 1. And then the next one is the molar mass of the compound, which is going to be 115.9 right there. And then I go back to kilograms, where 1 kilogram equals 1,000 grams. So when you put it on your calculator, it's going to be nothing more than 1 times to the third, multiplied by 10 to the third, multiplied by 1, multiplied by 1, multiplied by 115.9, multiplied by 1, divided by 1, divided by 55.85, divided by 1, divided by 1, divided by 1,000. And that will give us our results in kilograms of the compound. So that's how we approach this type of problem. So here's your daily work. And once you do that, we can say that we now know how to go from moles of a compound to the moles of the elements that make the compound. We also know how to go from grams of the compound to the grams of the elements that made the compound, which means we have to go from grams to moles, moles of one to moles of the other, and then grams of the other. So from the compound to the element, or vice versa, like we just did. And with that said, we're done with part C. So when we come back to part D, we will start talking about percent composition, and then we will finish up on part E with empirical formulas. And that will cover all the lectures for this week number 7. See you later. Take care.